So, hello everyone. My name is Ananya Chowdhury. I have recently cleared my UGC-NET exam in the June 2024 cycle. So, this class today has been brought to you by PsyAcademy India. So, this topic, that is the Weber's, Fechner's, and Stevens' laws, come under the 5th unit of our syllabus of psychology, that is attention, perception, learning, memory, and forgetting. So if we start with the basics of this topic, these laws, they come under psychophysics. Now psychophysics is a field that talks about the relationship between some stimuli, the properties of some stimuli, and the sensory experiences that these stimuli they evoke. So it talks about their relationship. And one important point here is that the founder of psychophysics was Sir Gustav Theodor Fechner. Now, if we talk about thresholds, because that is also an important part of what we are going to discuss later. So thresholds, so there are many stimulus in the environment, but we do not detect all of them. But the smallest stimulus that we can actually detect of any kind of, it can be of any kind, but the smallest stimulus that we can detect is basically called threshold. Now, thresholds are majorly of two kinds. The first one is absolute threshold, and then we'll talk about different thresholds. So, absolute threshold is basically the minimum amount of a stimulus that one can detect 50% of the time. Here it is assumed that, let's say, there are 100 trials of an experiment. So amongst those 100 trials, it is expected that around 50% of the times, that is 50 times of those 100 trials, you will detect the stimulus. So the minimum amount of a stimulus that you can detect 50% of the time is called our absolute threshold. Now it is also known as absolute Lyman. Now Lyman here means threshold. Now the second type of threshold is called difference threshold. It is basically the amount of stimulus, of a particular stimulus, that you increase or decrease, that you add basically to the initial stimulus, such that the person can finally detect that there is a difference in the stimulus. Now again, the person is able to detect this difference on 50 trials. So 50% of the times the person can detect. So the amount that a stimulus must be increased or decreased for a person to notice the difference in the stimulus 50% of the times is called the difference threshold. Now other terms for this difference threshold would be, one is difference Lyman, and the other one, and very important one here, would be just noticeable difference, JND. Now we will use this term later on as well, so we need to remember this. It's called JND, just noticeable difference. So difference threshold is also known as just noticeable difference. Now to understand this concept of thresholds, I have kept this example here. So let's say you take a glass of water and you keep adding sugar to it. So initially you ask some person, your friend or whoever, you ask them that, can you detect the sweetness of the sugar, of the water? And of course they have to taste it and they say no. But then you keep adding sugar to it and you keep asking them after every teaspoon, let's say, and finally, let's say after the 4th teaspoon, they finally detect that yes, that they can detect the sweetness of the water. So the moment that they first noticed the change in the sweetness would be the absolute threshold here, and the amount of sugar that was added for them to notice a change. Let's say after adding 4 tablespoons of sugar, they can finally detect that there is sweetness. So this amount would be called the difference threshold. Now finally we come to our topic. So the first law that we are going to talk about is the Weber's law. So this law was given by Ernst Weber in 1834, and it states that the JND of a stimulus, it is proportional to the initial intensity of that stimulus. We can study this through this formula that we have mentioned here. It's delta I upon I equals to K. So the word proportional is what we need to remember here. Now in this formula, the delta I, it stands for the change in the stimulus intensity, which is basically the JND. Now delta here, some of you might be aware that it represents change. So delta I stands for the change in the stimulus intensity, and this I here is basically the original intensity, the original stimulus intensity, or the original stimulus basically, and the change in that original intensity is denoted here by delta I, and K is a constant. Now one important thing to notice here is K, which is basically delta I upon I, is called the Weber fraction. So this is something might not be very difficult to understand, since this is the Weber's law, if you remember the formula. So delta I, K is equal to delta I upon I. So this entire term is called the Weber fraction. This is the Weber's law, and this is a fraction, which is obvious. So this is called the Weber's fraction. Which one? Delta I upon I, which is equals to K, and K is a constant, which is also known as the Weber fraction. So in the Weber's law, we basically see that how much JND is actually necessary to notice a change. It basically depends on the original stimulus, the initial stimulus, how strong it is, weak it is. That decides how much JND, delta I, difference threshold, whatever you want to call it, how much the initial stimulus is, decides how much JND is necessary to notice a change. So this is our Weber's law. Now to understand it further, I have kept an example here. So yeah, so in this example, let us say initially we take a small weight, let's say 100 grams, and the Weber fraction, it has been calculated before that it is around 0.04. Let's not go into a lot of detail. So let's say 4% or 0.04 is the number for K here. That is a constant that we said, which is the Weber fraction. Okay, so for 100 grams, let's say a small weight of 100 grams, the change in weight that you can actually notice, the JND, is 4% of 100. Well, let's not go into the details here. Basically, as we saw that the value of K is 0.04, which has usually been calculated that it is 0.04 for weight. Now our weight, our initial stimulus is 100 grams. So our I is 100 and our K is 0.04. So if we look at this formula here, if we cross multiply, so delta I upon I equals to K. Now if we cross multiply, we get delta I equals to K into I. So our K is 0.04, as we can see here. it's delta I equals to 0.04 into I, which is 100. So we get 4 grams. So basically, even if we don't get the exact calculations here, the basic thing that we need to understand is that if someone adds delta I, that is 4 grams here, so 4 grams of weight, that is 4 grams of weight to the 100 grams, that is when you will notice a change in weight. Now next, if we talk about a larger weight, let's say 200 grams. Now for 200 grams, our K, our Weber fraction, it will remain constant because constants never change, so it will remain 0.04 only. Our I has become 200 grams. So now if we put it in the Weber's formula, we get that our delta I is 8 grams because 0.04 into 200, that is 8 grams. So basically for 200 grams of weight or stimuli, you notice a change when 8 grams of weight is added to the 200 grams. So if we summarize what we understood from this, and I hope we did understand this example. So we saw that as the original weight gets larger, the change required for us to detect that change also becomes larger. But the ratio, that is the K, that is the Weber's fraction, it remains constant at 4% or 0.04. So basically we saw that for a small weight, that is for 100 grams, the JND was 4 grams, but for 200 grams, it was 8 grams. So this shows that the JND is proportional to the initial stimulus. The K is constant, but it keeps the JND, it keeps increasing depending on the initial stimulus, but in a constant manner. Now if we so now we'll talk about the Fechner's law. Now Fechner's law was given by Gustav Fechner. It talks about the relationship between the stimulus and how we sense it. So the Fechner's law says that the strength of the sensation, how we perceive, how much we can perceive the stimuli, so that strength, it grows logarithmically as the intensity of the stimulus increases. So basically there is a logarithmic relationship between the stimulus and how we perceive it. We can understand this better through this formula, this Fechner's formula, where this formula given by Fechner's instead, where S equals to K multiplied by log I, that is log of I. Now here I is our initial stimulus, our physical stimulus intensity, whatever you want to call it, basically our initial stimulus. K is again a constant here in the Fechner's law, but again a constant which depends, which varies from stimuli to stimuli. Now S is our subjective or perceived magnitude of the sensation, how much of the stimulus we are able to perceive, in what way. We will understand this better again through an example. So we are taking the example of light in a room. So for, let's say, firstly, for low intensity light or dim light, suppose the initial intensity is low and let's say it's on some scale of brightness it's 10. So I, that is our initial stimulus, it is 10. Now using the Fechner's law, and again K here, now we will take a very simple value, that is 1, so that there is ease of calculation. So our K is 1, our I is 10, let's say, and let's not focus exactly on the values, but we'll try to understand this in the end. So let's not focus too much on the numerical part. So what I mean is, let's say it's our value of I is 10. The k, for simplicity, we have taken it as 1. Now if we put it in the formula, S, that is how we are able to perceive, how we perceive the stimulus, S equals to k into log of I. Now if you had maths before, or even if you didn't, you might have heard about it or not. So basically there are log tables. I'm guessing you are aware of it. So we have log tables where there are fixed values for logs of different numbers basically. Now the value of log 10 is what we are concerned about here right now. So value of log 10, it's given that it's 1. So now, as I said, for simplicity of calculation, our k is 1. The value of log I, that is log 10, is 1. So 1 into 1 is 1. So now our value of S, that is how much of the brightness we are perceiving. So the perceived brightness is 1 here. So S is 1. Now if we increase the intensity of the brightness, now our I, let's say it's 100. We are assuming it. So since we increased it, let's say 100, because the value of log 100 is 2. It is decided, nothing to learn about, nothing to stress about. So the value of log I here, now I is 100, so log 100 is 2, and our k remains 1. So 1 into 2 is 2. So our value of S here, that is perceived brightness, is 2. Now in the third case, which is very bright light, higher intensity of light. So here our value of I, let's say it's since it's high intensity, so it's 1000. So here the value of log 1000 is 3. So we have 1 into 3, that is 3. So our value of S becomes 3. Now this is what is important, how we understand this example. So what I meant to explain with this example is that as the intensity of light, we saw it increase from 10 to 100, then to 1000. So when we increased it from 10 to 100, it was around a 10 times, not around, actually exactly a 10 times increase. Now when the intensity of light increases by 10 times, we see that the perceived brightness only increases from 1 to 2, which is minimal, bare minimum. So and now in the second case, when we saw that, rather the third case, we saw that the intensity, we increased it from 100 to 1000. There again a 10 times increase, but the perceived brightness only increases from 2 to 3. Now, so what we understand through this example is that the perceived brightness is increasing more slowly as the light becomes brighter. So the intensity of the light is increasing at a higher rate, but with the intensity or the speed with which the perceived brightness is increasing, that is very slow. So this is what is represented through the Weber's law. Since the perceived brightness increases in a logarithmic fashion, so that is at a very low rate. So now we talk about the Stevens law. Now the Stevens law was given by Stanley Stevens in 1957, and he said that the relationship between the perceived stimulus, the perceived sensation, and the initial stimulus, it's not always logarithmic. Instead, he said that the relationship can better be described as a power function. So he said that the perceived intensity of the stimulus or of the sensation, it can be described as being proportional to the stimulus, the initial stimulus, raised to a certain power, that is denoted by n here. So the perceived stimulus is the perceived sensation, is basically described as the stimulus raised to the power to a certain power. So here it is described by a formula, that is S equals to K into I to the power N. Now S is again the subjective magnitude of the sensation, or basically the how you perceive, the sensory perception, okay, how you perceive the stimulus. That is our S, which can be subjective. It can vary from person to person. Our I is our stimulus intensity, or our initial stimulus, as we saw in the previous two cases as well. K is again our constant, and N here would be the exponent that again depends on the stimulus, the particular stimulus. So here we have our formula. Now we'll again take an example to understand this better. So let's take the example of the pain that we get from an electric shock that we come across. Let's not hope it ever happens, but so let us take N here, because electric shock is something, it can be of it can be very dangerous. You can feel it with high intensity, and you know it. So that is why we are taking this is just an example, this is simply an example. So we are taking N as, let's say, 3 here. So 3 is basically, if you take it as a power, so you are increasing the pain cubically. The perception of pain, actually it will increase cubically. So we will not say 3 times, but cubically. So it is a huge number. So N we have kept as 3, because there is supposed to be we are expecting a larger increase in the sensation of pain due to electric shock. Now again K, for simplicity we are keeping it as 1. Now here let's say in the first case, our initial intensity is intensity of electric shock is, let's say, 2. So our I equals to 2. Now so our I is 2 here, and if we put our values K, which is 1, which we took for simplicity purpose, I we took as a low intensity electric shock, which is 2. So we put it in our formula, where S equals to K into I to the power N. Now N we took it as 3, because electric shock can be intense. So when we put it in our formula, we get 1 into 2 to the power 3, which is 8. So for an intensity of 2, I equals to 2, which is a mild electric shock, the perceived pain we might experience is 8 here. This is just an example. I would like to repeat this. Now in our second case, we increase the intensity of the the electric shock. Now I here would be 4. Let us assume. So we put the values again in the formula. Now K is a constant, so it remains 1. N is again constant, an exponent but constant, a power but constant. So it was 3. So we put it in a formula, so it becomes 1 into 4 to the power 3, and this becomes 64. So the value of our S is 64. Now finally, if we increase the intensity again, now our I becomes 8. So for a value of 8, for electric shock of 8, of intensity 8, we put the values again in a formula. K is constant 1, N is again constant, the power, that is 3. So we have 1 into 8 to the power 3, that is 512. So let's focus on how it is increasing and not the exact numerical values. Now yes, so we come to the important part here, how we will infer, how we will conclude what is happening here. So we see that the perceived pain, that is S, it increases dramatically as the intensity of the stimulus increases. So here the value of N was 3, and we saw that the relationship of the physical intensity of the shock and the perceived pain is cubical, because it's n to the power 3, sorry, n is 3. So this means that small increases in the intensity of the electric shock will lead to large increases in the perceived pain, which we can understand here. So for we have for I equals to 2, we see that the perceived pain was 8. For I equals to 4, we have an 8-fold increase in the intensity of pain, the perceived pain, which now becomes 64, s equals to 64. And when we keep the value of I as 8, the value of s becomes, again there is an 8-fold increase, that is 512. So by 8-fold it means 8 times. So there is an 8 times increase in the intensity of pain, while there is a little increase in the intensity of electric shock. So we see that in the case of pain perception here, the Stevens power law with n equals to 3, that is cubical increase, indicates that pain sensation increases much faster, as we saw in this example. It's not a hard and fast rule, but we saw it here that the sensation of pain increases much faster than the physical stimulus intensity. So the sensation is increasing, as we saw, 8-fold times as compared to the initial case, the previous case, although the intensity of pain is not increasing at that rate. Sorry, the intensity of the electric shock is not increasing at that rate, but the sensation is increasing 8-fold times, 8 times. So this is what is represented by the Stevens law. So it increases at a higher rate, which is almost opposite to what was shown in the Fechner's law, because that was increasing logarithmically. Here it is increasing as a power, as an exponent. So if we summarize what we studied today, so our Weber's law, so when we solve questions, we have to focus on the keywords, because we do not have a lot of time in the exam. We have to keep a target of around 1 minute at the most for questions that are not very easy. So we cannot keep a lot of time for each question, so we have to focus on the keywords. So although we have to read the question once, twice, as many times as is possible in those 1 minute, in the 1 minute, but keywords are very important. So to summarize, we see that the Weber's law, we saw that the Weber's law focuses on a proportional relationship between the JND and the original intensity. The Fechner's law, it focuses on a logarithmic relationship between how we perceive the stimulus and the original intensity of the stimulus. And the Stevens power law, now it is called the power law only. So the Stevens power law, so it becomes easy to understand that that how you perceive the stimulus depends on a power function, on exponent of the initial stimulus, a power of the initial stimulus, that gives us how we perceive the stimuli. Now here I have kept a PYQ. Although this is a very old question, it was as we can see, it was asked in the 2013 December cycle, but you never know when they might ask it again, since it is part of the syllabus. So here, if you have solved the question, PYQ questions before, or if you have attempted the exam before, you will know that these kinds of questions, match the followings, are pretty common. And so here you have to relate or rather match the list 1 with list 2, which is very obvious. And here below the table there are codes given, so you have to match them. So in the first list we see PQRS, and the second one we see there is numbering, so we have to match them, and the correct matched pair would be your correct answer. So let's take around or rather I would say you can pause the video, solve the question, and then in the next slide we will discuss the answer. So also I'd like to mention here that the first point, that is the signal detection theory, has not been taught. It was not part of our topic today. We'll learn this later on. So let's do the question. You can pause it and then I'll show the answer. So now our correct answer is D here. So signal detection theory we will not talk about. It's the second option. We'll let it go. But the Stevens-Parr law, as we see, it's the fourth option, because as we see the keyword here, that the stimulus is raised to a par, so it becomes a Stevens-Parr law. Very easy. Now the Fechner's law is, as we already studied today, logarithmic function, and Weber's law would be the first option that remains. It would have become easier if we had already studied about signal detection theory. So we'll study about these other topics later on. So we come to an end of our class today. So I would also like to mention that this was a free class, or a demo class you could say, for our classes that we take of UGC-NET. So we are currently enrolling students, aspirants who want to give the UGC-NET exam for this upcoming June 2025 cycle. So enrollments are open. You can register. If you like my teaching, do like, comment, share, and all the details for enrolling have been shared on the PsyUni Facebook as well as Instagram account. So thank you. Have a nice day.